September 19, 1940. The Wardman Park Hotel, Washington, D.C. Rain drummed against the windows as British physicist Edward Taffy Bowen opened a locked metal deed box and carefully lifted out a device the size of a dinner plate. The dozen American scientists and military officials crowding the hotel suite fell silent. Bowen placed the object, cavity magnetron serial number 12, on the conference table. "This," he said quietly, "produces 1,000 times the microwave power of anything you have." The Americans stared. Their best klystron tubes generated 10 watts. This British device generated 10 kilowatts. From 10 centimeters of copper and wire, enough concentrated energy to detect a surface submarine from miles away in total darkness. The head of the U.S. Navy's microwave research program later confessed he wanted to personally carry the magnetron to safety himself, afraid someone might trip and destroy what historian James Finney Baxter III would call the most valuable cargo ever brought to our shores. But technical brilliance meant nothing if it couldn't be produced. Britain's General Electric Company had managed to manufacture exactly 12 prototypes in 3 months. The 13th sat on that hotel table. RAF Coastal Command needed thousands, immediately to stop German U-boats from starving Britain into surrender. The United Kingdom simply didn't have the industrial capacity. They were manufacturing 17 cavity magnetrons per day, barely enough to equip 2 aircraft squadrons per week, while losing 300 merchant ships per month to submarines hunting in wolf packs across the Atlantic. At that production rate, radar would arrive too late to matter. By conservative military estimates, Britain had perhaps 9 months before starvation forced capitulation. The mathematics were brutal, the timeline impossible, the stakes civilizational. What the men in that Washington hotel room didn't know was that solving the impossible production problem would fall to a 46-year-old electrician from Maine who had never graduated from grammar school, never taken a single engineering course, and never been told what couldn't be done. The situation facing the Allies in autumn 1940 bordered on catastrophic. German U-boats prowled the Atlantic with near impunity. In September alone, they sank 59 merchant vessels, totaling 295 to 335 tons. Convoys leaving North America faced a gauntlet of submarines that attacked primarily at night, when lookouts were blind and conventional radar was useless. Admiral Karl Donitz's Wolfpacks had refined their tactics to devastating effect. Surface at night, approach convoy using diesel engines, torpedo multiple ships, submerge before dawn. The strategy worked because no existing technology could reliably detect a surfaced submarine in darkness from sufficient distance to mount an effective attack. British scientists had developed impressive long-wavelength radar systems. The chain home network had helped win the Battle of Britain, but these massive installations operated at 1.5 meters wavelength. While adequate for detecting aircraft at long range, they couldn't provide the resolution needed to spot small targets like submarine conning towers against wave clutter, especially from aircraft. Physicists understood that shorter wavelengths would solve the problem. Microwave radar operating at 10 centimeter wavelength could distinguish a submarine from ocean surface returns, work from aircraft, penetrate fog and darkness, and provide accurate enough range information to guide attacks. There was just one seemingly insurmountable obstacle. Generating sufficient microwave power required a cavity magnetron, and cavity magnetrons were extraordinarily difficult to manufacture. The technical challenges were formidable. Traditional magnetron construction demanded that skilled machinists spend weeks hand-drilling 8 precise cavities into solid copper blocks, each cavity requiring tolerances measured in thousandths of an inch. Internal components had to be laboriously soldered with delicate wires connecting microscopic elements. Assembly required specialized equipment, experienced technicians, and meticulous quality control. Every step was slow, every step was expensive, every step was prone to failure. Britain's leading electrical firms had tried everything: improved training programs, better tooling, more skilled workers. Nothing substantially increased output. By October 1940, production had reached 17 completed magnetrons per day across all British manufacturing facilities. To equip Coastal Command's patrol aircraft, much less supply the Royal Navy, Bomber Command, and eventually American forces, would require thousands per day. The consensus among production engineers was unequivocal. Large-scale magnetron manufacturing was technically impossible with existing methods. Colonel John Cockcroft, one of Britain's most respected physicists and a member of the Tizard mission, summarized the situation in his classified October 1940 report. The cavity magnetron represents our best opportunity to turn the tide against submarine warfare. However, current production methods cannot scale to meet operational requirements. Even if we doubled or tripled manufacturing capacity, we would fall short by an order of magnitude. We require a fundamental breakthrough in production technique that may not be achievable. The American engineers who examined the device at MIT's newly formed radiation laboratory reached similar conclusions. One Bell Telephone Laboratories production specialist noted after studying the British magnetrons, "This is a remarkable scientific achievement. From a manufacturing standpoint, it's a nightmare. Mass production using current methods would require training thousands of precision machinists, building hundreds of specialized facilities, and accepting failure rates exceeding 50%. The timeline to achieve necessary production levels, 36 months minimum. The Allies didn't have 36 months. They probably didn't have 12. Into this crisis stepped an unlikely problem solver. Percy Spencer was a 46-year-old self-taught engineer working as chief of the power tube division at Raytheon Manufacturing Company in Waltham, Massachusetts, who had never attended university, never studied engineering formally, and never been exposed to orthodox thinking about what was possible. Born on July 19, 1894, in Howland, Maine, Spencer was orphaned before he could walk. His father died when Percy was 18 months old. His mother, unable to cope, sent him to live with his aunt and uncle. When Spencer was 7, his uncle died. The boy and his widowed aunt traveled around New England, surviving on whatever money she could earn as an itinerant weaver and whatever odd jobs young Percy could find. He left school after 5th grade, aged 12, to work dawn to dusk in a spool mill. At 16, hearing that a local paper mill planned to install electricity, Spencer spent his evenings learning everything possible about electrical systems from whatever sources he could scavenge. When the installation crew arrived, he talked his way onto the team despite having zero formal training. He learned entirely by trial and error and studying at night. The 1912 Titanic disaster proved a turning point. Spencer, fascinated by wireless telegraphy's role in the rescue efforts, joined the U.S. Navy at 18 to become a radio operator. During night watches aboard ship, he taught himself calculus, trigonometry, physics, chemistry, and metallurgy from borrowed textbooks. "I just got hold of a lot of textbooks and taught myself while I was standing watch at night," he later recalled. After World War I, Spencer joined American Appliance Company in Cambridge, soon renamed Raytheon, bringing a reputation as a man who could make a working tube out of a sardine can, according to one MIT physicist. His approach differed fundamentally from university-trained engineers. Where they saw insurmountable technical barriers, Spencer saw problems waiting for practical solutions. A 1958 Reader's Digest profile captured the difference. An MIT scientist observed, "The educated scientist knows many things won't work. Percy doesn't know what can't be done." By 1939, Spencer had become one of the world's leading experts in radar tube design, despite, or perhaps because of, his complete lack of formal engineering credentials. When Raytheon won the contract to work with MIT's Radiation Laboratory on cavity magnetron production, following the teasered mission, Spencer was the obvious choice to lead the effort. The British scientists had provided detailed technical specifications, manufacturing drawings, and their best guidance on production methods. Spencer studied them carefully. Then he put the documentation aside and examined the magnetron itself, turning it over in his hands, taking it apart, rebuilding it, testing each component. Within days, he understood something the British experts had missed. They were manufacturing the magnetron wrong. The British approach treated magnetron production as precision instrument craftsmanship. Spencer recognized it should be treated as mass manufacturing. The insight sounds simple in retrospect. At the time, it was revolutionary. Traditional magnetron construction required machining 8 precision cavities into a solid copper cylinder, a process that took skilled workers days to complete and frequently resulted in costly errors. Spencer proposed eliminating machining entirely. Instead, stamp out thin cross-sections of copper using a punch press, the same technology used to manufacture automobile body panels. Stack these stamped sections together. Fuse them in an oven using a conveyor belt system. The result? A complete magnetron cavity block produced in minutes rather than weeks, requiring minimal skill, generating consistent quality, and costing a fraction of traditional methods. The British scientists were skeptical, to put it mildly. Dr. Eric Megor, General Electric Company's vacuum tube expert, who had designed the prototypes Spencer was proposing to radically alter, expressed polite but firm reservations during a transatlantic consultation in late 1940. Mr. Spencer's approach, while admirably pragmatic, overlooks several fundamental technical requirements. The cavity dimensions demand tolerances of plus or minus 0.002 of an inch. Stamped metal cannot reliably achieve such precision. Furthermore, the copper purity and surface finish specifications exist for essential performance reasons, not mere preference. Altering the fundamental construction method risks compromising the magnetron's operating characteristics. MIT Radiation Laboratory Director Lee Dubridge, a distinguished physicist who had enthusiastically embraced the magnetron project, also harbored concerns. According to laboratory meeting minutes from November 1940, Dr. Dubridge questioned whether manufacturing shortcuts proposed by Raytheon's Mr. Spencer might achieve production volume at the cost of performance degradation. Given the magnetron's critical importance, committee recommends prioritizing quality over quantity in initial production phase. But Spencer wasn't proposing shortcuts. He was proposing fundamental redesign. He replaced precision-machined copper bars with stamped copper laminations. He eliminated laboriously hand-soldered internal wires by substituting a simple, solid ring. He designed specialized fixtures that ensured stamped sections aligned perfectly during stacking. He developed a conveyor belt furnace that brazed the stacked layers into a solid block with consistent, controlled heat. Most radically, he reconfigured the entire assembly sequence to employ unskilled workers performing simple, repetitive tasks, rather than craftsmen executing complex procedures. The first prototypes emerged from Spencer's pilot production line in December 1940. They worked. More than worked. They matched the performance of hand-machined British units while requiring 95% less production time and 70% lower per unit cost. Spencer had proven the concept. Now came the real challenge: scaling from prototype to mass production. Raytheon's power tube division employed 15 people when Spencer took over in 1939. Throughout 1941, as his magnetron production system moved from pilot program to full operation, the division exploded in size. By December 1941, when America entered the war, Spencer supervised over 1,000 employees. By mid-1942, the number exceeded 3,000. By war's end, 5,000 workers operated production lines Spencer had designed, producing not 17 magnetrons per day like British facilities, but 2,600. The transformation from 17 to 2,600 represents a 153-fold increase, or approximately 15,000% production gain. Spencer achieved this not through incremental improvements to existing methods, but through wholesale reinvention of the entire manufacturing process. The production lines he created resembled automotive assembly more than precision instrument craftsmanship. Women with no prior technical experience operated stamping presses that punched out copper laminations with consistent precision. Other workers stacked the stampings into specialized alignment jigs. Conveyor belts carried stacked assemblies through carefully calibrated furnaces. Automatic test equipment verified performance specifications. The entire sequence from raw copper stock to finished magnetron ready for installation took hours instead of weeks. More importantly, the system proved robust. British hand manufacturing methods suffered failure rates approaching 60%. More than half of completed magnetrons failed to meet specifications. Spencer's mass production approach achieved failure rates below 4%. Not only could his lines produce 150 times more magnetrons, but 96% of them worked properly on first test. Before we continue with how Spencer's magnetrons turned the Battle of the Atlantic, I need to ask you something important. If you're enjoying this deep dive into how one self-taught electrician transformed the course of World War II through manufacturing innovation, make sure to hit that subscribe button and turn on notifications. This channel brings you untold stories of ordinary people who accomplished extraordinary things through persistence, ingenuity, and refusing to accept that problems were unsolvable. Your support helps us keep researching and producing these detailed historical narratives. Now, let's see what happened when Spencer's mass-produced magnetrons began reaching combat units. The impact proved immediate and decisive. Throughout 1941, RAF Coastal Command aircraft equipped with ASV Mark II radar operating at 1.5-meter wavelength achieved limited success against U-boats. German submarines quickly developed warning receivers that detected radar emissions from beyond the aircraft's detection range, allowing U-boats to dive before being spotted. By late 1942, U-boat commanders had regained the initiative. Admiral Dönitz's Wolfpacks sank merchant shipping faster than Allied shipyards could replace losses. Britain's food situation grew critical. Military strategists estimated the nation had perhaps 6 months' emergency reserves remaining. Then, in February and March 1943, Spencer's magnetrons enabled deployment of ASV Mark III centimetric radar. Operating at 10-centimeter wavelength, these new radar sets were invisible to German warning receivers, which only detected signals at meter wavelengths. For the first time since 1941, Allied patrol aircraft could detect surfaced U-boats before the submarines detected the aircraft. The results were devastating to the German submarine force. March 6, 1943. Bay of Biscay off the coast of France. Squadron leader Jefferson Greswell piloted a Coastal Command Wellington bomber equipped with one of the first production ASV Mark III radar sets, powered by a Spencer-designed magnetron, on an anti-submarine patrol. At 0217 hours in complete darkness, his radar operator reported contact at 12 miles range. Greswell reduced altitude and increased speed, approaching the target while maintaining radar lock. At 2 miles, the aircraft's lead light, a powerful searchlight designed to illuminate targets during final approach, snapped on, catching U-boat U-333 fully surfaced and apparently unaware of the aircraft's presence. The German submarine's lookouts had heard nothing, seen nothing, received no radar warning. the Wellington released 4 depth charges from 150 feet altitude. All 4 struck within 20 yards of the submarine's hull. U-333 survived that attack with severe damage, limping back to base with 14 casualties, but the encounter marked a turning point. Over the following weeks, similar attacks multiplied across the Atlantic. U-boats that had hunted convoys with impunity now found themselves hunted. Submarines surfacing to transit at night, standard procedure that allowed diesel engines to recharge batteries and provide high-speed positioning, began disappearing without trace. German naval intelligence struggled to understand what had changed. Their radar warning receivers showed nothing unusual. British transmission patterns hadn't altered. Yet somehow Allied aircraft were achieving night intercepts against surfaced U-boats with uncanny accuracy. The numbers tell the story. In the first quarter of 1943, before widespread ASV marked the third deployment, German U-boats sank 627,377 tons of Allied shipping while losing 24 submarines, approximately 26,000 tons, sunk per U-boat lost. In May 1943, when Spencer's magnetrons equipped most coastal command patrol aircraft, Allied shipping losses dropped to 264,152 tons, while 43 U-boats were destroyed. Approximately 6,000 tons per submarine lost, a 77% reduction in U-boat effectiveness. By summer 1943, the Battle of the Atlantic had decisively turned. Admiral Dönitz, writing in his war diary on May 24, 1943, captured the German Navy's confusion and despair. "We are facing an enemy whose scientific capabilities have rendered our submarine force ineffective. He has achieved superiority not through superior tactics or strategy, but through technology we cannot counter. Our losses have become unsustainable. Until we develop adequate countermeasures, we must withdraw from the North Atlantic convoy routes." The withdrawal essentially conceded defeat. From summer 1943 forward, Allied convoys crossed the Atlantic with minimal losses. Britain's food crisis evaporated. American troops and equipment flowed to England without significant interdiction, enabling the D-Day invasion. The submarines that had nearly won the war for Germany were neutralized by radar operating at wavelengths only cavity magnetrons could generate, and only Spencer's production methods could manufacture at the scale required. Commodore Jennings Dow, head of electronics at the U.S. Navy's Bureau of Ships, summarized the contributions succinctly. Raytheon radar had a marked effect on every major sea engagement of the war. The impact extended far beyond anti-submarine operations. Spencer's mass-produced magnetrons powered airborne intercept radars that allowed night fighters to hunt German bombers attacking British cities. They enabled H-2S ground mapping radar that let Allied bombers navigate and strike targets in total darkness or through cloud cover. They provided fire control systems that dramatically improved anti-aircraft effectiveness against German V-1 flying bombs. By war's end, Raytheon had manufactured approximately 80% of all magnetrons used in American and British radar systems, more than 2 million individual units. Each one incorporated manufacturing innovations Spencer had pioneered. Each one contributed to shortening the war. Post-war analysis by military historians consistently identifies radar as among the 3 most significant technological advantages held by the Allies, alongside code-breaking and nuclear weapons. Unlike those highly classified programs, radar's contribution was immediately obvious to those who employed it. Bomber crews flying through flak-filled skies over Germany knew their H-2S navigation systems, powered by Spencer's magnetrons, allowed accurate bombing when weather grounded the Luftwaffe. Destroyer captains pursuing submarines in North Atlantic gales knew their Type 271 surface search radar, powered by Spencer's magnetrons, could detect U-boats in conditions where lookouts saw nothing. fighter pilots intercepting enemy bombers at midnight knew their AI-marked intercept radar, powered by Spencer's magnetrons, made the crucial difference between contact and empty sky. A 1946 study by the U.S. Strategic Bombing Survey attempted to quantify radar's contribution to Allied victory. The analysis concluded that microwave radar availability accelerated war termination by approximately 12 to 18 months, compared to scenarios where only long wavelength systems existed. 12 to 18 months translated directly into lives. Fewer casualties, fewer cities destroyed, earlier return to peace. The study noted, the rapid deployment of centimetric radar, made possible only through unprecedented production scaling, proved decisive in multiple theaters. Without mass-manufactured cavity magnetrons, microwave radar deployment would have been delayed until 1945 or later, potentially extending the European War into 1946 and requiring invasion of the Japanese home islands. Recognition for Spencer's contribution came swiftly, if quietly. The U.S. Navy awarded him its highest civilian honor, the Distinguished Public Service Award, in 1943, though wartime security prevented public disclosure of why. Vannevar Bush, who as director of the Office of Scientific Research and Development oversaw the Manhattan Project, radar development, and dozens of other war programs, knew precisely what Spencer had accomplished. Bush later said Spencer earned the respect of every physicist in the country, not only for his ingenuity, but for what he has learned about physics by absorbing it through his skin. Coming from Bush, who worked with Einstein, Oppenheimer, and virtually every prominent American scientist, the compliment carried weight. Spencer's friends included General Omar Bradley, William Hewlett, David Packard, and Bush himself, men who had changed the world through their respective contributions. They recognized in Spencer a kindred spirit, someone who solved problems others considered insoluble, not through superior resources or credentials, but through insatiable curiosity and refusal to accept conventional wisdom about limitations. Spencer held 300 patents by the time he retired. Most involved improvements to vacuum tubes, radar components, and microwave technology. He became senior vice president and member of the board of directors at Raytheon, despite never having completed grammar school. Rising from the three-person startup he joined in 1925 to leadership of a corporation employing thousands. The irony was not lost on Spencer that his lack of formal education probably helped, rather than hindered his most significant achievements. The MIT-trained physicists who initially doubted his magnetron production redesign knew too much about why certain approaches couldn't work. Spencer, unburdened by that knowledge, simply tried things, observed results, and iterated until he found what did work. His characteristic response when encountering problems: let's tinker and see. That attitude, treating obstacles as interesting puzzles, rather than immovable barriers, defined both his approach and his success. Spencer's most famous invention came after the war, in 1945, when he noticed a candy bar in his pocket had melted while he stood near an operating magnetron. His curiosity about why led to experimentation. He tried popcorn kernels, which promptly popped. He tried an egg in a kettle, which exploded in a colleague's face when they leaned in for a closer look. He realized microwaves could cook food. By 1947, Raytheon was manufacturing the first commercial microwave ovens. Massive, expensive units that found limited initial market. But the principle was sound, and over subsequent decades, microwave ovens became ubiquitous. Today, over 200 million are in use worldwide. Everyone traces lineage to Spencer's wartime magnetron work. For this invention, which transformed how billions of people prepare food, Raytheon paid Spencer exactly $2. the standard gratuity the company provided all employees for patents assigned to corporate ownership. The $2 payment symbolizes something important about innovation during wartime. Spencer wasn't motivated by financial reward. He earned reasonable compensation as a Raytheon executive, but his drive came from solving problems that mattered, from knowing his work contributed to victory, from the satisfaction of making impossible things work. In an era when innovation is often discussed primarily in terms of disruption, market advantage, and wealth creation, Spencer's story offers a different model. Ingenuity applied to urgent problems because they need solving. Recognition consisting mainly of respect from peers who understand what was achieved. Legacy measured in lives saved and history altered rather than fortunes accumulated. Percy Spencer died on September 8, 1970, in Newton, Massachusetts, age 76. Microwave ovens were still expensive novelties in 1970. Today, they're in 90% of American homes, and the number approaches that globally. Radar, the technology Spencer made mass-producible during humanity's darkest hour, has evolved into systems that track aircraft crossing continents, guide cars through traffic, map ocean depths, monitor weather from space, and enable dozens of applications he never imagined. Every modern radar system, from the device in a police speed gun to the phased arrays protecting against ballistic missiles, employs descendants of the cavity magnetron Spencer learned to manufacture at scale when everyone said it couldn't be done. The building Raytheon named in his honor still stands at the company's Woburn, Massachusetts facility. An early radar-range microwave oven sits in the lobby across from the cafeteria, a reminder that the same technology developed to detect enemies can later serve peaceful purposes. But perhaps the greatest memorial to Spencer exists in something more fundamental: the principle that determined ingenuity matters more than formal credentials. That impossible often means nobody's tried the right approach yet. That curiosity and persistence can overcome obstacles that stop more conventionally educated minds. The lessons transcend the specific technical problem Spencer solved. Modern innovation challenges: climate change, pandemic response, sustainable energy, artificial intelligence safety, present seemingly impossible obstacles. Teams addressing these challenges include thousands with advanced degrees and sophisticated tools Spencer never dreamed of. Yet his story suggests they need something else as well: the willingness to question assumptions about what's possible, the courage to propose solutions others dismiss as impractical, the persistence to iterate through failures until discovering what works. Spencer's transformation of magnetron manufacturing teaches that breakthrough innovation rarely comes from perfecting existing methods. British engineers working to improve traditional magnetron production techniques would never have achieved 153-fold gains through incremental optimization. Revolutionary improvement required someone willing to reject the entire conventional approach and reimagine the problem from first principles. This pattern repeats throughout history. Real breakthroughs come not from better execution of established methods, but from fundamental reconceptualization of the problem itself. It teaches that formal education, while valuable, can sometimes limit creative problem-solving by instilling too much respect for conventional wisdom about what works and what doesn't. Spencer's lack of engineering degree meant he approached the magnetron production problem without preconceptions about proper vacuum tube manufacturing techniques. He saw a copper device that needed producing in quantity, recognized similarities to mass manufacturing problems he'd solved before, and applied those lessons without worrying about whether vacuum tubes were supposed to be manufactured that way. It teaches that crisis can be a powerful catalyst for innovation. Spencer possessed his unique combination of skills and perspective years before World War II, But the urgent need to scale magnetron production provided the specific problem that required exactly his capabilities. Without that catalyst, he might have continued making incremental improvements to photoelectric tubes. The war's existential stakes created both opportunity and permission to attempt radical solutions that wouldn't have been considered during peacetime. It teaches that impact matters more than credit. Spencer received his $2 patent payment, his Navy award, recognition from peers, and a building with his name on it. But the millions who survived the war because radar shortened it never knew his name. The billions who use microwave ovens daily don't connect them to magnetron manufacturing innovation during World War II, and Spencer seemed perfectly content with that. He knew what he'd accomplished. Those who mattered, Bush, Bradley, Hewlett, Packard, the physicists and engineers who understood the significance, knew what he'd accomplished. That sufficed. Most profoundly, it teaches that ordinary origins predict nothing about extraordinary capability. Percy Spencer, orphaned before he could walk, educated through 5th grade, working in a spool mill at age 12, possessed intelligence and ingenuity that surpassed the vast majority of university-trained engineers. Society nearly missed benefiting from his capabilities because conventional pathways into technical fields required credentials he'd never had opportunity to obtain. Only Raytheon's willingness to evaluate him based on demonstrated ability rather than formal qualifications allowed his talents to find appropriate application. How many other Percy Spencers existed, and still exist, whose potential was never realized because they lacked the right credentials, the right connections, the right opportunities? When you use a microwave oven to heat coffee, you're benefiting from technology pioneered by a man who taught himself physics while standing night watch aboard a Navy ship in 1913, reading borrowed textbooks by lamplight. When you pass through airport security, where radar systems scan for threats, you're protected by descendants of the technology Spencer made mass-producible when Britain faced starvation and America raced to mobilize. When you use GPS navigation, that depends on sophisticated electronics and timing systems developed from wartime radar research. You're employing tools made possible because one self-educated engineer refused to accept that 17 magnetrons per day was the maximum achievable production rate. September 19, 1940, the Wardman Park Hotel, Washington, D.C. Edward Bowen placed cavity magnetron number 12 on that conference table and told the assembled Americans it could generate unprecedented microwave power. True enough. But the device itself, brilliant as it was, couldn't win the war. It couldn't even help until somebody figured out how to manufacture thousands of them. The British scientists who designed it couldn't solve that problem. The American engineers who initially studied it couldn't solve that problem. The problem required someone who didn't know it was impossible, who wasn't constrained by orthodox thinking about precision instrument manufacturing, who could look at a copper cylinder and see stamping presses and conveyor belts and assembly lines instead of skilled craftsmen with jeweler's tools. The orphan from Maine, the boy who left school at 12, the man who taught himself physics from borrowed textbooks while standing watch at night, turned out to be exactly the right person for exactly that problem at exactly that moment in history. Percy Spencer proved that impossible is often just another word for nobody's tried it my way yet. The magnetron that saved millions of lives was manufactured not despite Spencer's lack of formal education, but perhaps in part because of it. His ignorance of why it couldn't be done freed him to discover how it could be done. Today, when you encounter a problem that seems impossible, when experts explain all the reasons why something can't work, when conventional wisdom says the obstacles are insurmountable, remember Percy Spencer. Remember that the man who transformed World War II's most critical technology didn't have an engineering degree. Remember that breakthrough innovation often comes from those who don't know what can't be done. Remember that 17 per day became 2,600 per day because one electrician looked at the problem differently. The impossible became possible because one person refused to accept it couldn't be done. That's how radar helped win the war. That's how millions of lives were saved. That's how the world changed, because a fifth-grade education turned out to be exactly enough.